All right, we're going on with section 5.5, the gravitational force and weight. The gravitational force and weight. All right, the picture there is, I first thought it was Acapulco diver. It's not, it's from Mazatlan. It's a Mazatlan cliff diver. Not as high as the Acapulco cliff divers. It's only 50 feet, but the water they dive into can be as low as 6 feet. So you have to time it just right with the waves. Okay, let's get on with the lecture. All objects are attracted to Earth. The gravitational force F sub g is the attractive force exerted by Earth on any object. It's directed toward the center of the Earth, and the magnitude is called the weight of the object. Now, freely falling object experiences acceleration g acting toward the center of the Earth. Applying Newton's second law to freely falling object of mass m, we get the force of the sum of the forces equals ma, the mass times acceleration. We substitute g for a, and we get the force equals the gravitational force. So force equals mg. The gravitational force equals mg, the mass of the object times the gravitational acceleration, which we use 9.8 meters per second squared. The weight of the object is simply the scalar value, and it's just mg, no vectors involved. Okay, let's see. G varies with geographic location. Who would have thought that? But it's true. G varies with the weight, the gravitational acceleration G varies with geographic location. G decreases with increasing distance from the center of the Earth. So an object weighs less at higher altitudes than at sea level. For example, a 1,000 kilogram pallet of bricks used in construction of the Empire State Building in New York City weighed 9,800 newtons at street level, but weighed about 1 newton less by the time it was lifted from the sidewalk level to the top of the building. Example, a student has a mass of 70 kilograms. His weight would be 686 newtons. At the top of a mountain, where G is, let's say, 9.77 meters per second squared, his weight would be 684 newtons. The equation indicates clear difference between mass and weight. So mass is an inherent property of all objects, and the weight is that mass times the gravitational acceleration of the location. So you take the 1 kilogram mass here on Earth is different. It's the same mass on the moon, but it's going to weigh less because the gravitational acceleration is 1/6 the gravitational acceleration here on the Earth. So let's y'all are too young. I remember it. I remember Neil Armstrong's first stepping off the lunar module onto the surface of the moon. We all watched it. It was a big event when I was a kid. So the life support unit strapped to the back of an astronaut Harrison Schmitt weighed 300 pounds on Earth and had a mass of 136 kilograms. During training, a 50-pound mock-up with a mass of 23 kilograms was used. It simulated the reduced weight of the unit on the moon. It did not correctly mimic the unchanging mass. It's more difficult to accelerate the 136 kilogram unit on the moon than it was to accelerate the 23 kilogram unit on Earth. The equation quantifies gravitational force of an object. It does not require the object to be moving. Even for a stationary object, for the object on which several forces act, the equation can be used to calculate the magnitude of gravitational force. The result is a subtle shift in the interpretation of M in equations. M in the equation determines the strength of gravitational attraction between the object and the Earth. So the inertial mass versus gravitational mass, the role is completely different from that previously described for mass, measuring the resistance to changes in motion in response to external force, the inertial mass. M in this equation is equal to the gravitational mass. The experimental conclusion in Newtonian dynamics is that gravitational mass and inertial mass have the same value. G varies from one planet to the next, the magnitude of gravitational force, mg, but the inertial mass, in other words, just to get something moving, if it has more inertia, even though it's lighter, it won't want to move, just its inertial mass. It has more inertia. Let's do a quick quiz. Suppose you're talking by interplanetary telephone to a friend who lives on the moon. He tells you that he has just won a Newton of gold in a contest. Excitedly, you tell him that you entered the Earth version of the same contest and also won a Newton of gold. Who's richer? Who has more gold? Is it you, your friend, or it's both the same? Your friend is. Why? Because the value of G is smaller on the moon than on the Earth. More mass of gold would be required to represent 1 Newton of weight on the moon. Therefore, your friend on the moon is richer by a factor of 6. It takes 6 times the mass to equal 1 Newton. What would be a 1 Newton here on Earth? Okay, 1 Newton would be about 0.1. It would be about 100 grams. Okay, let's see. You have most likely been in an elevator that accelerates upward as it moves toward a higher floor. In this case, you feel heavier. In fact, you were standing on a bathroom scale at the time, and the scale measures a force having a magnitude that is greater than your weight. Therefore, you have tactile and measured evidence that leads you to believe you are heavier in this situation. Are you heavier? And the answer is no. No, your weight is unchanged. Your experiences are due to your being in a non-inertial reference frame. To provide the acceleration upward, the floor or scale must exert on your feet an upward force that is greater in magnitude than your weight. It is this greater force you feel, which you are interpreted as feeling heavier. The scale reads the force with which it pushes up on you, not your weight, unless you're at rest, and so its reading increases. Okay, this ends our discussion of the gravitational force and weight. Next, we will discuss Newton's third law.